In aviation, what is the angle of attack? So for a wing section, the angle of attack is normally the angle between the chord line and the relative wind, the free stream airflow well away from the wing, and the chord line is normally a straight line from the leading edge to the trailing edge. That's well understood, no problem there. But what if you have a wing section with a deflected flap or aileron or a leading edge device? To define the angle of attack, should we now define a new chord line to join the leading edge and trailing edge or not? That's the question I want to look at here. Why raise this question? Because the concept below can now be found in some places with a new chord line being defined whenever a flap is deflected. Now here's one important reference book, Theory of Wing Sections, Abbott and von Dönhoff, with lots of theory and data on hundreds of wing sections. So what does it say? It says that the chord line does not change when any high lift systems are deployed. And that's the best practice in aeronautical engineering as a whole. And this has been a fundamental principle for decades, from the very beginning, as far as I know, from when high lift devices were invented for experimental testing and for analysis with CFD. An example here from Abbott and von Dönhoff showing one wing section with a plain sealed flap that varies from -15 to +65, and as the flap is deflected downwards, the CL increases, generating more lift for the same speed, and the stalling angle reduces slightly, as you can see. But that chart, like thousands of others, is based on the principle that the chord line for defining alpha does not change as the flap is deflected. And a couple of tables from the same textbook. And the right-hand column shows the alpha at CL max, which is the stalling angle, effectively. And so you can see the effect of different flap configurations. But again, it is all based on the chord line not changing when flap is deflected, and this makes it very easy, keeps it simple, makes it easy to compare different configurations. So the newer alternative concept certainly does not match established best practice in aeronautical engineering. Using best practice, you would say that the flaps, when the flaps go down, the camber increases, but the angle of attack is unchanged in these two pictures. So that's for a wing section only. What about a complete aeroplane? So this is an explanation from Boeing, and I put the reference there on the page. So Boeing explains that the longitudinal axis, the x-axis, is widely used as the reference line in the aircraft industry for angle of attack, and it's not just for large jets, it's for turboprops and many other planes. And so that's the reference line, and it does not change when the flap and slat configuration changes. And here we have a chart for a complete aeroplane showing lift coefficient versus angle of attack, alpha, showing the effect of flaps and slats. So as you deflect the flaps, the CL increases, the CL alpha curve moves up, and as you extend the slats, the CL alpha curve is extended to the upper right, the stalling angle increases, and there's a small reduction in stalling angle when flaps are deflected. So this is a common presentation, but it, like many other charts, is based on the principle that the chord line does not change as the flaps or slats are moved. Now, from another aspect, you can measure angle of attack. For many years, alpha vanes have been used to measure angle of attack, and the alpha vane is counterbalanced and aligns with the local airflow, and the angle of attack is measured from the longitudinal axis of the airplane. Always, in my experience, and there is never any adjustment to this measured angle of attack when flaps or slats are deployed. Now alpha vanes can be used to trigger a stall warning system or a stick shaker or a pusher, and the alpha at the stall will typically vary with the flap and slat positions, so the flap and slat configuration is normally input into the system so that the warning or shaker or pusher action can occur at the appropriate angle of attack. Now, what about a complete wing? So normally the wing section shape is defined carefully at the wing root and tip, defined by X over C and Y over C points, many points. The Y over C might be labeled Z over C, but the Y over C equals 0, the section reference line may not be a true chord line. You might find that. But the local wing section reference line, whatever it is, it does not change with flap or aileron movement. And it's normally compared to the aeroplane longitudinal axis. So you might say that the wing is mounted with the reference line at plus 2.5 degrees at the root and minus 0.5 degrees at the tip. So that's how it's mounted on the fuselage or with respect to the longitudinal axis. So that would be 3 degrees of twist, washout, and the wing root angle, so 2.5 degrees in this case, would be known as the wing incidence. And then the local wing angle of attack at any spanwise location, you can define that as the if you need to or want to, as the angle between the free stream airflow and the local wing section reference line. So in conclusion, this newer alternative concept which changes the chord line depending on flap and slat position is contrary to the established best practice in aeronautical engineering. And it's also contrary to best practice in flight operations where angle of attack is measured. And so I suggest this newer alternative concept should be avoided at all times. It adds no value and introduces confusion, in my view. Some references there and a brief resume for me, just for context. Thanks for watching.